spacecraft comms for the relay satellite. The relay satellite is going to be launched out of the Baikonur Cosmodrome on a Proton Breeze M launch vehicle. The Proton was chosen for its cost effectiveness and ability in providing the necessary escape energy in order to put our relay satellite onto its transfer trajectory to the moon. Once the launch vehicle provides the additional velocity, or delta V, in order to put the relay satellite on this trajectory, the satellite will separate from the launch vehicle and perform any necessary sensor calibration to account for any disturbances in alignment that might have happened during launch. While the satellite is transferring, it is going to be undergoing a 10-day transfer, and during this time it will be spin stabilized at a rate of 1 revolution every 10 minutes. This was done for thermal reasons and also to conserve fuel. The solar panels, which are sized for the on-station operations, only require 1.75 square meters of area in order to spacecraft. That means we will be cycling our batteries, but the overall depth of discharge on the batteries is only about 60 watt-hours, which is not close to what we would be doing to the batteries while we are on station and having to use them. So the primary power will come from that undeployed solar panel during transfer. Reflectors will remain stowed since they will not be in use during transfer, and also to minimize the structural impacts we would have if we were to fire the insertion engine with them deployed. Communication with the Earth throughout this phase will be done with 4 omnidirectional bicone antennas located there. There's 2, one on the anti-Earth base, and then there is another one on that base. For the insertion, the relay satellite will have to provide an additional delta V required in order to insert it into the desired trajectory in order to reach the halo orbit. This was modeled as an instantaneous delta V under the assumption that the time taken to perform the burn was small relative to the overall time of transfer. In order to accomplish this, we broke the burn up into a number of discrete burns spanning the course of approximately 2 hours. And taking into account engine limitations such as the maximum number of thermal cycles for the engine, as well as the maximum burn time for the engine, brought us to the methods analyzed in order to put the relay satellite into its halo orbit, and the particular method we chose was to use a stable manifold transfer, which I will go into further detail in the GNC section. Behind the solar panels? Yeah. If you look at it from the side, there's some clearance there, so it should be able to see out.
Is it supposed to be an omnidirectional antenna?
Yes.
It looks like it's made to cut the omnidirectional, but for some reason it looks like the solar panel made to cut the block. Is that an issue? Maybe some of the others picked up for it.
Chris?
Yes.
Do you know what the limitation is on the field of view for the omni antenna?
It's a 360 bicone that...
I was actually asking about the partial blockage by the solar array from to the side of some of them. So if this one is partly blocked in that direction, there's another one picking up on the side, so you still have full
coverage? Yeah, that was the layout of our system, where if one's partially blocked, you can pick it up on a different face.
So that was taking into account the fact that all panels are probably
yeah, and the layout of the relay satellite. I don't know.
Okay, once the relay satellite reaches re-axis in order to maintain a fix on the Earth and the Moon, and...
Another question. So you spin stabilized, what about principal axis?
we'll be spinning across Earth anti-Earth axis. As was shown.
Principal moment of inertia.
That, Ryan, is principal our Earth anti-Earth?
Yeah. Or during transfer, yes.
Yes.
We have
So,
Now, if you spin about the minimum moment of inertia, it will be unstable.
right.
Not after that. I don't know that's the issue here.
Our principal axis is Earth anti-Earth, and we're spinning about it. Right,
Is that
Ryan?
maximum moment of inertia?
It's maximum, right?
It's maximum at full field capacity.
The offset reflectors and castorine dishes will have their launch locks removed, and they will deploy as well. Communication at this time will still be performed through the omnidirectional antennas, which won't be blocked as much anymore with all of the reflectors and solar arrays deployed. The relay satellite will establish communications with them through use of the castorine dish. As Chaz will go into a bit more detail later, there is a small window through which they will be communicating. This was chosen over trying to attempt omni-to-omni communications, which would be far too costly in terms of power in order to get a surface and set up the array. The relay satellite will use the closed-loop auto-tracking system that Chris was mentioning in order to locate the positions of the hoppers. This is using the monopulse method, which uses a single signal on one of the hoppers in order to locate the position. Multi-tracking, which uses a combination of signals from all the hoppers simultaneously. A problem with this was that if the beacons on one of the hoppers went out, it would be reporting an inaccurate signal for location of the array, and the other method was Moon or Earth was generated. This resulted in a total eclipse time of approximately 4 days over the course of 15 years, with a maximum eclipse time of 13 hours. That 13 hours would define the longest amount of time that the relay satellite would be required to operate on batteries at minimal power. And also there was an average eclipse length of approximately 3 hours. And for this, when the batteries were designed to accommodate the 13 hours of minimal operations, this provided enough operations time for full transmit at approximately 4 hours. This is not taking into account the 2-cell failure scenario on the batteries. If 2 cells go out and we lose 2 strings accordingly, then we only have 2.5 hours. Scenario we have where if we go into, for example, our maximum eclipse time, and then for some reason we happen to enter our emergency scenario immediately afterward, there is an operational phase where we can effectively shut off most of the spacecraft. We'll be cycling communications equipment rather than putting it on standby, and that'll provide us with up to 40 hours of standby power and up to 25 hours accounting for the 2-cell out. So on top of the 13 hours, we'd have 12 or more. Dean?
That's including the 13-hour eclipse.
Right. Oh, okay. Including.
So you have 12 left?
Yeah.
You've got a reasonable amount of time there.
I think we were talking about was the emergency scenario. Yes.
So trying to operate these eclipse, that driving power system a lot?
For maintaining the 3 hours of operation, it did not drive the design of the power system, because when the power system was designed for the minimal operations at 13 hours, it also provided us with that amount of full operational time. So it was not a designing factor. This scenario occurs when the relay satellite either loses its communication with the Earth or somehow becomes disoriented and is unable to find the Sun. And during this phase, the ADCS and CDH systems will be working to first try and reacquire the position of the Sun, and then once it does that, its secondary task is to reacquire communication with the Earth if it indeed has lost that communication.